Hello friends, let us resume our discussion on one category of the mineral processing technique which we refer to as liberation. So this process of liberation, as the name indicates, it involves or it separates a desired mineral from the gangue mineral or the impurities that surround it. Now, given the way a mineral is formed and often the location where it is being formed, the minerals are largely surrounded by the impurities that is not of interest to us. This we refer to as gangue mineral. Now, given that this gangue mineral is present in a large quantity and it surrounds our desired mineral, the first step towards mineral processing involves liberating or separating this desired mineral from the surrounding gangue minerals. Now, this is done in liberation by breaking down the large mineral particle that is mined out into smaller fragments. Now, this process of breaking down the large mineral particle into smaller fragment, we refer to it as technically as comminution. Now, we have seen a purely theoretical case, an ideal structure of this mined mineral. This mined mineral in form of a large particle, how it looks like, in order to primarily understand different terminologies. So in our previous lectures, we have considered a mined particle of this form, where our desired mineral is rather localized, it is confined to a specific position and it is encapsulated by the gangue mineral. So this theoretical consideration, or a rather straightforward consideration, we were able to offer, or we offered, because we wanted to learn some terminologies, we wanted to understand certain terminologies. So these terminologies include tailings. These tailings are nothing but particles that exclusively comprise of gangue, and these are discarded once they have been identified. So we considered a purely straightforward particle, a larger particle, in order to understand certain terminologies, certain words that are referred, or certain terms that are used to refer the smaller particles. One of which is tailings. The tailings, they largely or primarily they comprise of, in case of the theoretical consideration, it exclusively comprise of the gangue mineral, and these are often discarded. The other is middling. They comprise of both minerals and gangue, and the way a tailing is treated after the initial comminution is different from how a middling is treated. And finally, we have our mineral particle, which is subjected to subsequent techniques that leads towards the final step of rendering the desired material. So our theoretical consideration helped us to understand these different terminologies, and secondly, they also helped us to understand how liberation works. So what is the ideal process flow that is involved in liberation? So we saw that in case of liberation, it begins with comminution, that is breaking down of a larger mined particle into smaller pieces, and this would give us these three smaller particles, which is tailing, middling, and our mineral particles. So while this mineral particle is what we desire and is taken up for further processings, a different set of processing, the tailing is being discarded, and it is the middling that is subjected to a second round of comminution, and thereby it would increase the amount of minerals that is being liberated from the whole of the mined particles. Now, the reason we follow this particular flow process or process chain, this flow chart, is because, of course, it is possible for us to initially get into these finer particles so that we are able to liberate sufficient amount of minerals. However, that is expensive when in the terms of the monetary resources that is being involved. So the amount of or the greater the finer the end product of the comminution is, the greater is the monetary expense that is being involved, and therefore we will have such a flowchart where we iterate the process of comminution and we restrict the second degree of comminution to middling alone and not we subject the extensive comminution at the initial stage. So we go for two-stage comminution instead of a one-stage comminution, wherein at the end of it we get smaller particles, because even though at the end the amount of mineral that is being liberated is going to be the same, the two-stage process is economically more optimal and when compared to the first stage, and also it helps us govern the overall flow of the overall process chain. What we mean by that is, we saw in the previous lecture, when we consider the practical aspects of this comminution or liberation, there needs to be a balance between few things. First thing is amount of a few aspects. The first aspect is the amount of mineral that is being liberated. So that is our primary goal, and that is we need to achieve it that in the greater amount. Secondly, even though our primary goal is to liberate the minerals, it should not be at the expense of a greater degree of monetary resources. So we should be able to make some profit out of it, and therefore there needs to be a balance between the amount of mineral that is being liberated by continuous comminution and also the money that is being spent. And finally, the ability to handle this comminuted or fragmented minerals also comes into play. We need to be able to handle this minerals in a comfortable manner. This comminuted or fragments of the minerals or the fragments of the middlings in a comfortable manner. So there are three aspects that we need to consider when we are talking from a practical standpoint when we are planning our process chain. So the first aspect is the amount of mineral that is being liberated. We saw there is a way to quantify it, that is called as degree of liberation. So we need to understand what is the degree of liberation that we are able to achieve through this particular process chain. Secondly, in order to achieve this process chain, in order to achieve this degree of liberation, how much monetary resources is being spent. And thirdly, we cannot keep on going or keep on reducing the size of the particles, even though it might increase the degree of liberation, because it affects the ability to handle the fragments, and therefore this factor of handling the fragment comes into play. So we need to consider these three factors when we are planning the process chain of the liberation. So one critical factor here is, even though it is possible for us to arrive at a uniform size of the final particles and thereby increasing the degree of liberation, we never do that. We impose only the middlings to the second level of comminution. By doing so, we have, of course, at the end we will have a non-uniform distribution, size distribution in the end fragments, but this will save our expenses. So that's the reason why, instead of reducing from the initial stage alone the particles that come out of this comminution, we plan it in such a way that we undertake 2 or 3 stage comminution. So we just subject middling to the subsequent comminution, not impose a comminution that directly renders us the small particles. So this is done exclusively for the sake of our economic benefit. Now, these are the concepts that we learned when we exclusively considered a setup such as this, a theoretical particle such as this, wherein our mineral was localized within a given larger particle which is encapsulated by the gangue mineral. So this type or this schematics of a mined particle wherein the gangue surrounds the mineral is very rarely observed in a physical condition. So when you consider a physical condition, the way the mineral is distributed within a larger mined particle is quite different. So it might be of rather ill-defined form such as this, and it might be intertwined with the gangue and appear as small pockets such as this, and of course it is also possible that it appears in the form of a well-defined localized structure such as this. So we need to make a difference between how practically a particle that is being mined out consists of a mineral and our theoretical consideration. So the theoretical consideration was a simplistic schematic that helped us understand the process chain that is involved in the comminution and different terminologies. However, we need to get to the practical form of these large particles in order to understand the practical difficulties that we face or practical aspect that we need to consider when we are planning the process chain. So the theoretical consideration, it helped us to understand the terminologies and the different way we need to, or a specific way rather, we need to approach the problem or the process of comminution. The specific way is that we cannot directly reduce the larger particles into very fine particles, even though it might increase the degree of liberation. We cannot do that because that is expensive. So what we do is we separate the larger particles into these tailings, middlings and the mineral particles, and then we subject only the middlings to the subsequent comminution. This way it is economically beneficial. So this is something that we learned by considering the rather straightforward schematic particle that comprised of, or that wherein the mineral was centralized and it was located in a very restricted region. And it also, such consideration also helped us to understand certain terminologies. Now we have to consider the practical, or how this particular, the larger particle that we mine out, how the mineral is distributed within this particle. And if you look into it, it is not rather localized, but it is distributed, and even the distribution is not of similar form. The form of the mineral that is associated with a particle, a larger particle, will be different. It can be of a random morphology, it can be of a definite morphology, or it can be intertwined, something like this. It completely interlocked, something like this, or something like you see here, where the minerals are in the form of small pockets. Now we saw in the previous lecture that when we subject a larger particle such as this, or for subject this larger particle into comminution, then the end product that we get will be of this form, wherein in addition to the free particles that comprises largely of minerals, let me use another color to be consistent. So in addition to the free particles that comprise of minerals, or exclusively comprise of minerals, and gangue, the other middlings will adopt a different form. The locked particles, as opposed to the free particles, they adopt a different forms. For instance, the locked particle may comprise of predominantly the minerals, or as opposed to this, the locked particle might comprise predominantly of the gangue. And thirdly, it is also possible that nothing, both mineral and gangue, they do not dominate, they are present in a considerable amount in one form of this locked particle. And finally, we also have a middling, wherein the way the mineral is observed is similar to the way it is present in the actual larger structure. So essentially what we have is, in addition to the exclusive mineral particle and exclusive gangue particle, we have different forms of middlings. So these are what we refer to as the free particles. So let me use what we refer to as the free particles, and these four are the middlings. And the middlings, they are of a very different forms, and we have two different middlings, contrasting middlings. One is that predominantly comprises of the mineral, and other which predominantly, or the amount of mineral in the second form of a middling is marginal. So let us refer to that as the first one as A and the second one as B. And in case of the third one, it is our rather typical middling, which comprises of more or less the equal amount of mineral and gangue. And finally, we have another form of middling, say D, where the form of mineral that is, or the form of minerals that is present in this fragment is similar to the one that is present in the actual larger particle. So in addition to these free particles, we also have middlings that can be categorized into four. Now, we saw in the previous lecture that if we consider a physical particles such as this, a physically mined out particle such as the one here, then the amount of particles that is exclusively made of mines or minerals, rather, that is one that is exclusively comprised of gangue, it's very rare. So given the nature of the distribution of minerals in a physical condition within a given large particle that has been mined out, the amount of free particles that we get from comminution is considerably low. So the free particles that exclusively comprise of one gangue or mineral alone. So it should either be comprising of minerals or it should be comprising of gangue. So such free particles, the amount of it will be considerably reduced when we consider a physical condition, a physical nature of the larger particle that is being mined out. So because of this random distribution of a mineral within a particle that is being mined out, because of this reason, what essentially we find is that the amount of free particle is significantly reduced. So therefore, in order to avoid the subsequent or in order to avoid subjecting the predominant portion of the middling. So what we essentially have is, when we subject such a mined particle in a physical condition, so you have a mined particle such as this, that is something that you often observe. So what essentially you would observe it when you consider the increasing order of the different particles, the least will be the free particles, and the greater amount of the particles will be the middlings. So if you consider our previous workflow, the one that we see here, it is the middling that is subjected to subsequent comminution in order to liberate the mineral that is locked in. So middlings are nothing but the locked particles. So in order to liberate that is being locked in this locked particle, that is being encapsulated in this locked particle, we subject this middling to subsequent comminution. Now, when we adopt the same approach, it means we are subjecting a significant portion of the particles into subsequent comminution. So what it means is that we are considering the comminution for a huge number of particles again, and this means that the amount of money that we will be spending on this will be higher. So it will also correspondingly increase. So what essentially it means to impose or to consider all the middlings that come out of this a practical or a physical particle such as this is that we are ultimately introducing almost all of the fragments that come out of the first comminution into second comminution. So let me repeat, following this flow chart for the physical case that we have here means you initially arrive at some fragments, and what you are essentially will be doing is, since in this fragment middling it dominates the volume fraction, so you will be imposing this large volume fraction of middling or subjecting this large volume fraction of middling into the second comminution or the second fragmentation. So it means that what basically you are doing two comminutions for the same amount of particles, and this means that the amount of money that is being spent, it is increasing. So in order to avoid that, what is being done in the physical from a practical standpoint on an industrial scale, what is done is these middlings are looked into, they are studied, and an acceptable degree of mineral or gangue is calculated or it is decided. So it varies of course depending on the minerals that we want. So but irrespective of a mineral that we are considering, an acceptable degree of mineral within a given particle is being decided upon, and depending on it, the A and B is either discarded or treated as a free particle. So let me repeat, when you fragment a mined out particle in a physical condition, predominantly you will end up with middling. And now when you have fragments which predominantly comprise of, which for say more than 90% that comprise of middling, now when you follow the theoretical flowchart that we have considered, then this 90% of the fragments again needs to be subjected to comminution. And when we do that, it is like considering the whole particle over again, now in smaller fragmental forms. Now when we do that, what essentially is happening is the amount of money that is being spent is increasing, it's being doubled here. So in order to avoid that, an acceptable level of mineral or gang is decided upon. So an acceptable level of mineral is decided upon for A, and an acceptable level of gang is decided upon for B. Now, when this acceptable level of mineral is equal to or greater than in A, so let us assume this acceptable level of minerals to be rather AM, if in the middling A, if the acceptable level of minerals AM is greater than or equal to. So the amount of mineral in A is greater than or equal to the acceptable level of minerals, then in that case, so if this condition is satisfied, in that case A is treated as a free particle. So instead of subjecting all the middlings to subsequent comminution, you agree upon, you decide or determine an acceptable level of minerals or gang. In case of the middling A, it is acceptable level of minerals. So when the amount of mineral in A is higher than this acceptable level or equal to that of the acceptable level, then it is treated as a free particle that is exclusively comprised of the mineral. So these two are treated as equivalents. So for that, you need to define an acceptable level of mineral. And similarly, you decide upon an acceptable level of gang. When the gang material that is present in the middling is greater, or rather it is predominantly it comprises of the gang, or so it operates similar to that of the acceptable level of mineral, so it is greater than equal to that of the acceptable level of gang, then again you would treat such the middling as free particle, and these two then would be equivalent. So what you essentially have is, you essentially, in order to reduce the amount of middling in a practical setting, in order to reduce the subjection of all the middlings to subsequent comminution, in order to ensure that you are maintaining the cost, the level or the amount of money that is being spent in the subsequent comminution. So in order to do that, in order to regulate the amount of money that is being spent into the comminution, you introduce an acceptable level of mineral or gang. So in case of acceptable level of gang, the amount of gang that is present in a middling like B should be greater than or equal to that level. So when it is greater than or equal to that level, then you will treat that middling as similar to that of the free particles. So to put it in simple words, when your middling predominantly comprises of a particular comprises of gang to a certain level or a greater than it, then you will treat it as a free gang particle, and the same goes for the mineral particle. When your middling comprises of a considerable amount of mineral or greater than it, then you treat it as free mineral particle, and by doing that we can now get rid of these two middlings and consider only these two for subsequent comminution. So you can get rid of these two category of middlings and consider only these two for the C and D for subsequent middling. So what essentially we are doing is, so how the overall process chain would change for a physical condition is, if you could recollect the initial process chain, it began with comminution, and the comminution it rendered as the free particles, that is minerals and middlings, and our tailings. So these we assumed, or because of our consideration, the middlings, because of purely theoretical consideration. So this is our theoretical understanding. Because of our theoretical consideration, the amount of middling was considerably low when compared to the free particles, that is the mineral particles and the tailings, and therefore the middlings were subjected to subsequent comminution. However, in physical case, the whole thing changes. So when you consider a physical setup or a physical condition, an industrial scale condition, then what happens is the comminution, it primarily renders middlings alone. So it primarily renders middlings alone. The amount of the free particles, be it mineral or be it the gangue or the tailings, they are considerably small. So that's the reason we will write it in a different color. So the mineral particles and the gangue, or rather tailings, they are significantly smaller. So when compared to the amount of middling, they are negligible. So what we essentially then do is, from the middling, we separate certain particles and refer to them as free mineral particles and the free tailings. So in the purely theoretical process chain, you introduce comminution, you arrive at these three particles, and the middling is of considerably small amount, you subject that middling to subsequent comminution. However, in the actual physical condition, in an industrial scale setup, or when you are essentially doing this process in a real mine, what you would end up doing is, you first introduce the comminution, and you will realize that the amount of middling that is being produced is extremely large or extremely dominant when compared to the free particles, be it a mineral particle or the tailings. And subsequently you subject the middling, then you will not subject the entire middling to the comminution. Instead of doing that, you would separate the middlings into minerals and tailings and the other middlings. So only after the separation you would introduce or subject this second degree middling to the comminution. So depending on your consideration, the process chain you follow will vary. So when you are considering a purely theoretical case wherein the position of the mineral is rather localized, and it is confined to a specific region, and it is rather concentrated in that specific region, then the amount of middling that is being produced after the first stage of comminution will be lower, and this middling can be subjected to subsequent liberation because it's in the lower quantity. However, that same flow chart or the same process chain cannot be followed in the physical case, because the first stage of comminution will give you a huge proportion of the middlings alone. When you compare the proportion of middlings to the free particles, it will be considerably small. So therefore you cannot subject this whole of the middlings to the second degree or the second level of comminution. So what you would essentially do is, you will study this middling and you will separate these middlings into or refer to specific middlings as the free particles by agreeing upon an acceptable level of minerals or gangues. So you define an acceptable level of minerals and gangues, and based on that you categorize the middlings into minerals and tailings. And once you have done that, only the remnant after this categorization will be subjected to subsequent comminution. So depending on the consideration, depending on the nature of the particle that you mine out, the process chain that is involved in the liberation would change. Now, it is possible that certain mined out particles have the features that is similar to our theoretical consideration. So in that case, the process chain would be of this form. When you have a mined out particle that is close to our theoretical consideration, wherein the mineral is rather localized and it is of a single form, then in that case the amount of middling will be lower and you can follow this process chain here. However, in most of the physical cases, most of the mined out particles, the mineral is not confined to a specific region. They are distributed and their forms are also significantly different. So in that cases, in order to be economically consistent or economically beneficial, we have to follow this technique. And here, for the separation of the middlings into mineral particles and tailings, we have to have an acceptable level of minerals or gangue. Now again, you can also restrict this to acceptable level of minerals alone and have different definition for categorizing minerals and tailings. So in that case, for minerals, it should be greater than or equal to. In case of gangue, when you consider just acceptable level of minerals, it should be less than or equal to. So instead of having acceptable level of minerals and gangue like we are considered in the previous slide, you can also restrict yourself to acceptable level of minerals when you have a greater, when you consider a particle that predominantly comprises of minerals, then the acceptable level of minerals should be greater than or equal to a specific value, then it can be treated as a free particle, free mineral particle. So when you have a middling wherein the predominant mineral is gangue, then the amount of the acceptable mineral or the mineral that is of desire to us is less than or equal to certain value, then we can treat it as tailing. So this is something that you can think and understand. So you can think about it for some time and understand how just by considering an acceptable level of minerals alone, we can distinguish minerals and tailings. Now, the reason we have considered these two different forms of mineral that wherein or the two different forms of the larger particle is for us to differentiate how the entire process chain changes. So if you could understand, or if you could look closely, the entire process chain, it depends upon the amount of middlings that are being produced. When the amount of middling is quite small, then you can subject the middling directly into subsequent comminution. If the amount of middling is significantly higher, or it is predominantly the middling that is present, then what we need to do is we need to identify certain middlings, we need to refer to or categorize certain forms of middlings as free particles, thereby reducing the fraction of middlings that is present and reducing the fraction of middling that is subjected to subsequent comminution. So this is what we saw in the previous lecture, and this is how we reduce the amount of middling that we will be handling or introducing in the subsequent comminution, and this is how the process chain changes depending on the amount of middling that is being produced. So you have two factors that govern the process chain. One is how the mineral is distributed within a given mined out larger particle, and secondly, amount of middling that is being produced. Of course, the particle distribution or the mineral distribution within a particle is governs the amount of middling. So ultimately, the only governing factor, if you consider the only independent factor, it is the middling, the amount of middling that is being produced after the comminution. It is the factor that governs the process chain that we adapt for the liberation process. Now, there are certain physical properties that are involved or that are associated with the larger particle that can be used for our benefit for the process of liberation. So far what we have seen is we have just broken down or fragmented a larger mineral particles into smaller fragments, and just by breaking down into smaller fragments, we were able to liberate a certain portion of the mineral particles from the overall larger particle that has been mined out. So that is what we have essentially been considering so far. So the whole entire process of liberation is just comminution or fragmentation, and this fragmentation, it separates it helps us get free mineral particle and free gangue particles and some middlings, and we subject the middling to subsequent comminution, and again we will be able to arrive at free mineral particles, free gangue particles, and the amount of middling after each cycle will keep on be reducing. It will continuously be reducing, and we will consider for the subsequent steps the mineral particles alone, and we'll be discarding all the tailing particles. So this is what we have been doing so far. Now, in addition to this, instead of subjecting the middling to comminution, it is also possible for us to use a different method or a different way to liberate the mineral that is associated with the gangue particle within a fragment. So, instead of subjecting the middling to subsequent fragmentation, we are now attempting to use certain properties of the middlings in order to separate the locked in mineral from its gangue. So far, we have not been considering any properties of the minerals or the gangue for that matter. We have not been considering any property of the overall particle, the mined out particle as a whole. We have just been considering or focusing on the process. This process is nothing but is just fragmenting a larger piece of the mined out particle into smaller ones. We have not rendered any consideration about the properties of the different minerals or the gangue that is associated with the larger particles. Now, we have seen that depending on the amount of middling that is being produced, the process chain that is involved in liberation changes. So irrespective of this process chain, the common factor here is we are subjecting the middling to subsequent comminution. Now, when we have a specific set of minerals and gangs, specific forms of minerals and gangs, instead of subjecting the middling to subsequent comminution, we can use their physical properties to liberate the mineral from the gang. So the properties that is responsible for that is that allows us to separate the mineral from gang without further comminution is the bonding between the minerals and gangs. Bonding between the mineral and gang. So what we have been essentially doing is, so far it has always been subjecting the middling to comminution in order to liberate the minerals. So depending on the amount of middling you get, you keep on introducing or subjecting this middling to subsequent comminution, and thereby reducing the amount of middling and increasing the amount of minerals, thereby subsequently increasing the degree of liberation. Now instead of doing that, we now focus on the bonding strength between the minerals and gang, and by studying this bonding strength, we will now attempt to liberate the mineral from its gang. Now most of the middlings, or by definition the middling comprises of a fraction of the desired mineral and a fraction of the gang. Now the property that we are interested in is the bonding strength between the mineral and the gang. The strength or the bonding strength that holds this particular particle or the fragment together. So the bonding strength between the mineral and the gang, and the strength that holds these two pieces of minerals together. So you have mineral and you have gang, and these are held together because of the strength in this region here, the strength in this interface here, the bonding strength between the mineral and gang. Now when the bonding strength between the mineral and gang is low, then it is easy or straightforward for us to introduce a specific form of a stress in this region and then break these particles into two and liberate the mineral from the gang. So when you have, or when the bonding between the mineral and gang is relatively low when compared to the bonding between mineral and gang particles, then you can impose a stress to the particle or the fragments, and this stress will create will break the weaker bonds between the mineral and gang, thereby liberating the mineral from the gang. So here you are not using any conventional comminution, you are not using any conventional fragmentation, but you are using or you are exploiting the property of this particle, this fragment here, which is the weaker bond between the minerals and gangs. So you are making use of the weaker bonds between the minerals and gangs, and using that you are fragmenting the mineral, or you are separating the mineral from gang. So this is referred to as liberation by detachment. Liberation by detachment. So far what we have seen is liberation by fragmentation or liberation by comminution. So this is what we have been considering so far. But liberation by detachment, it considers the properties of the minerals that we are considering, particularly the bonds between the mineral and the gang. Now the bond between mineral and the mineral, bond between gang and the gang, if it is greater than the bond between mineral and the gang. So the bond between mineral and the mineral will be here, so it will be associated with this region here. So this will be associated purely in the mineral section of this particle, and this bond between gang and gang will purely be associated with the gang section of the particle. And when the bond between the similar particles are greater, and when compared to the bonds between the non-similar or dissimilar particles, that is the bond between mineral and gang, then when you impose or expose this particular particle to a stress condition, then the weaker bonds they given before the stronger bonds. And since the weaker bonds are between mineral and gangue, then we are essentially liberating the mineral from its gangue, not by comminution, but by using its own properties and by introducing appropriate stress condition. Often for this case, the microwaves are being employed. So the microwaves are being introduced into these fiddlings in order to impose the stress on these particles, the desired stress on these particles, and because this stress, it helps or it acts on, even though this stress acts on all the different bondings, and since the bonding between the minerals and the gangue is weaker, this interface here, it gives in. This interface marked in red, it breaks off first before any other bonds break up. So this red region here, the interface, it breaks off, thereby liberating the mineral from the gangue. So this is what we refer to as the liberation by detachment, and this liberation by detachment cannot be used for all minerals because this depends on the properties of the mineral, particularly the bond strength between the minerals and gangue. So the liberation by detachment, it employs or it uses the one of the critical properties of a particle in order to liberate the mineral from the gangue. So, and we use microwaves as one of the factors or one of the source for the stress that helps us liberate or that helps us break the bond between the minerals and gangue. So essentially the liberation, it can be done in two ways. There is comminution, which never cares about the properties of a given mineral. If you don't know the behavior or the property of a given mineral, you can go for this comminution approach. You keep on breaking down the sizes of the middlings till you arrive at a decent degree of liberation. Now, if you know that a given mineral or a given large particle of a mineral, the bond strength between the minerals and the gangue is weaker when compared to the bond strength between two mineral particles and or rather two mineral entities and two gangue entities. So when I say between this BMM here, it refers to the bond strength between two mineral entities, and BGG refers to the mineral strength between the two gangue entities, and when these bond strength are noticeably higher than when compared to the bond strength between a mineral entity and a gangue entity, then you can go for liberation by detachment. And again, this is property dependent, and this cannot be employed for all the without any prior knowledge of the property of the mineral particles. This cannot be employed without the, or it cannot be employed for all the mineral particles. So if we employ it for all the mineral particles, then we cannot expect a clean breakaway of this interface here, and still essentially what we will be ending up with is fragmentation of the larger particles. Now instead of regular comminution, you will be using microwaves to do it, you will be using stresses to do it. So again, that will be economically a huge burden on us. So therefore, in order to, before adapting liberation by attachment, we need to understand the properties of the mineral and the gangue, particularly the bond strength between the mineral entities and the gangue entities. So this is all that is involved in the process of, this gives an overview of the process of the different processes that are involved in liberation. So far what we have seen is liberation as a whole process or a category of process that is involved in mineral processing. Now the overview of it is what we have seen so far. Now even though while considering this overview, there are few steps that were involved, particularly in these flowcharts, that is not typically of liberation. So even though we were considering an overview of the liberation, an overview of what this liberation involves, even though we were talking in that terms, all the steps that were involved in these process chains are not exclusively associated with liberation. So even in this process chain, there is also the second category of mineral processing that is involved, which is concentration. So in this process chain here, even though it is discussed, we discussed this in the context of liberation, it is not exclusively associated with the liberation. There is a concentration, the second category of mineral processing, which we are about to see, it is involved in this process chain as well. This concentration is nothing but the process of separating the different forms of the particles. Now we saw that comminution breaks down the larger particles into smaller particles. Now even after breaking down these larger particles into smaller particles, even though this liberates to some degree the locked in mineral from its gangue, these fragments will be helpful to us only when we are able to separate the middlings, the mineral particles and the tailing particles. So we can further perform any operation on the smaller fragments only when we are able to separate all these different category of particles. And this separation of all these different category of particles is what we refer to as concentration. So all the while we were talking about liberation, the concentration was implicitly involved here, here and also here. So what concentration does is, it helps us separate the fragments that come out of the comminution process, the fragments that comprise of all locked and free particles together. It is the concentration that separates these particles into mineral particles, tailings and middlings. But for this concentration, we will not have any set of particles to work on. All we will be having is all the different particles just mixed up together, a mixture of all the different particles. So it is, whenever we talk about this process chain, it is not just the liberation allowed, it is the combination of liberation and concentration. So concentration, what it does is, so when you talk about a technical definition of concentration, it separates the free mineral particles or close to free mineral particles from middlings and tailings. So essentially what you are doing is, you are increasing the concentration of the mineral in the set of particles that we have. So the definition of particles, or rather the definition of concentration is, the description of concentration is the process of separating the free mineral particles or close to free mineral particles from middlings and tailings. So when you introduce comminution to a larger mined out particles, you will get a mixture of both free particles and locked particles. Now when you separate out the mineral particles alone, you are essentially considering a subgroup of particles that possess a high concentration of the minerals, and that is what we refer to as the concentration, the process of separating out the minerals from the mixture of the different free and locked particles. Now when we are able to separate the minerals out from the bunch of the big mixture of these different particles, all we will be left with is middling and tailings, and we can modify the concentration process further in order to separate the middlings and tailings. So essentially it is the process of the concentration, it is the approach of concentration that helps us separate the end product of comminution into middlings, tailings and the mineral particles. And whenever we were considering this flow chart or this process chain of liberation, the process of concentration was implicitly involved in it. So in the next lecture we will look into what concentration involves, and with that we will be winding up this overview of the mineral processing, and we will get into the specifics of the process that we have been considering so far. So we will see ourselves in the next lecture. Goodbye.